So in this video, it's the second in the series. We're going to try to build this 27 megahertz radio control receiver from the Talking Electronics website. Those who saw the first video, we worked on the amplifier stage and built that, which I've got over here. And this part, we're going to try to deal with the microcontroller part, but rather than using this PIC chip, we're going to use a Arduino. And so in this video, we're going to put the code together. We're going to see if we can actually sample data coming out of the amplifier stage. And in the process, we're probably going to touch on my Arduino as an oscilloscope stuff. I will put chapter markers in so you can skip ahead if you need to. Alright, let's get started. Okay, so in order to be able to tell whether the Arduino would be able to extract the signal from the amplifier stages of the 27 megahertz receiver, thought I would go back to my Arduino Oscilloscope video series, because that oscilloscope function would be really useful for just seeing whether we can see the signal. So I'm going to video part 11, and I'm going down here now to the GitHub site for that version of the oscilloscope. And if we go in here we've got the source code, so I'm just going to plonk that into here to then download to my Arduino. Okay, and from memory so we've got 38400 baud rate, so let's just go to the serial monitor and see that it's outputting as we would expect, and it is, so that's good. So I think this is going to work with the spreadsheet, so now we need to go get that, and that will also be in the GitHub page. So I'm going to download the spreadsheet. Okay, we'll open that one up. We'll disconnect our serial monitor. That's really strange. Okay, so there seems that the trick is that you need to actually click on the file in GitHub and then use this download raw file here. And then if we open the file, it looks a lot better. And now we need to enable data streamer, which it looks like I haven't done on this laptop. So from memory, that was down in options, add-ins, there it is. So on the COM add-ins, then OK. Then we have our data streaming, that's good. And then we need to connect to our Arduino. I remember, if you didn't have this serial monitor disabled, this wouldn't work. Okay, and then I think we need to set the baud rate. COM3. How do we do that again? Start data. Okay, a reboot later, and we've got this data feeding up from the Arduino now. I think what I was also missing was in settings, I had to set the baud rate here, but this looked like it was grayed out, but I had to pick 38400 because that was what was in the code. So now we've got data feeding up, and if we look at our spreadsheet here, we can see the blue line with something on that coming in on port 1 or channel 1. Okay, so now what we've done is we've set up a trimmer pot with one end of the trimmer pot going to the 5-volt rail, one going to ground, and the swipe in the middle of the trimmer pot going to analog pin 0 on the Arduino. And if I look on the oscilloscope, we have a voltage sitting there, and then when I turn the trimmer pot here, you can see we're altering the voltage that's coming out. And if I turn it the other way, I guess it's going to go up. Yep. So I think we've got our oscilloscope working again. So now that we've sort of got the Arduino oscilloscope code working again, we're going to hook it up, or have actually. So for those that watched the first video, the amplifying stage from this 27 MHz transmitter was really this part here with the 3 transistors with an output here, and that in his diagram goes off to a PIC chip, but I'm going to be using the Arduino Uno, and where it's got pin 5 in the diagram there, that's going to be the analog pin 1 of the Arduino Uno. And I'm using the power of the Arduino and the ground from the Arduino to provide me my 5-volt supply, which is starting here and here, and then it flows up to these 2 points. And this is what it looks like hooked up. Sorry, it's a bit of a mess, but my Arduino, the circuit I built previously, the input of the signal gen is here, which effectively is this point here in the process going through this. As I said before, there's none of that front end stuff there, and we can see on the actual oscilloscope that we have the yellow signal representing the signal generator, providing a very small let's see, there's 20 millivolts per division there, so it's a very small amplitude signal, and then the output is giving me my 5-volt signal that is what we're wanting our microcontroller to be able to detect. And now if we go to the laptop here with the oscilloscope program running, we can see that it is also showing that same waveform. So everything's working, and I think we'll be able to use the Arduino to now do different things based on what frequency signal we provide, whether it's that 600 Hz or that 1200 Hz tone. One of the things I learned when I was creating the video series for the Arduino oscilloscope was that the digital read function that's just built in the Arduino ecosystem is actually quite slow, and there's also an ability to adjust the prescaler to improve the sampling speed. So in the last version of that spreadsheet and code in the Arduino, I've actually got it set to what was the default prescaler value, but I'm using the more efficient way of doing the sampling, where it calls an it runs in the background and then calls an interrupt. So with this and set with that basic original prescaler value of 7, when I'm generating a signal of 1200 Hz, there's not a lot of sample points that get recorded in one cycle, which you can see with the dots. There's not many dots there. So what it would be good is to work out a good prescaler value to use, such that we can capture a reasonable level of detail, but not blow out the memory of the Arduino with having too many sample points. What I'm going to do here is adjust the prescaler value while I've got the 1200 Hz setting on the signal generator. So let's try 6 as the prescaler. That captures a reasonable amount of dots. Let's go for 5. Okay, there it's fairly clear, so I think we'd be able to sort of see a rising edge measuring between a couple of points and count the number of times. Say with the 200 samples that we're taking here, we could say that if we're getting about 6 cycles in that sampling period, then we're at the 1200 Hertz setting. Let's just adjust the signal generator now to produce the 600 Hertz signal. Okay, and it looks like in this scenario, if we had about 3, we would know we were at the 600 Hertz. I might just experiment with the prescaler value set to 4. Yeah, so see here, if we have it set to 4 and we record 200 samples, we only really get 1 cycle at 600 Hertz. So I don't think 4 is a very good choice for the prescaler. If I go back to 6, that gives us about 6 cycles, and there's enough dots there that I think we're going to be sampling at a fast enough rate. But let's go up to the 1200 because I have a feeling that might have been a bit iffy. Okay, at the 6 prescaler value, we also can kind of see probably enough sample points, or at least on the rise of the signal, that we could probably detect the frequency there. So we'll either use 5 or 6 as our prescaler value. Okay, so now what I've done is I've gone and taken that original code that just outputs to the spreadsheet, and I have put in a threshold value, and I'm going to say at 2 volts, and then I'm going to count the number of times that the voltage rises from below 2 volts to above 2 volts through that threshold, and I do that after the 200 samples are taken each time. And then what I'm going to do is output to different digital pins based on whether there's 2 cycles, 3 cycles, 4 cycles, 5, etc. So that we got a visual feedback of, hey, can the Arduino measure the frequencies? So let's just jump into, we've got the spreadsheet going, and we are currently running at about 300 Hertz, and we get no lights on. And let's now boost the frequency a little bit. Now we're getting 2 to 3 cycles in the sampling period, and we can see our first LED comes on. And then if I boost the frequency a bit further, maybe take up to about 700 Hertz, now we get 2 LEDs coming on, and we're getting about 4 cycles in the sampling period. And then I can push it further, obviously take it up a bit further, and we'll get our third LED on, and that's about 900 Hertz. And we can go a bit further. Nothing yet, a bit further again. Okay, and now we're getting another LED on, and this one's a blue one, and this might represent, like, blue might be forward and red would be like backwards if it was a radio control car, for example. And I'll push it a bit further, and we'll just get the other LED to come on as well. So I think we can now take this code, or the bits that drive the LEDs at least, and we can have something that we can just have a do nothing or go forward or go back kind of algorithm to it, based on whether we've got the sort of 600 Hertz for backwards or the 1200 Hertz for forwards coming through in the pulses. Okay, so let's have a look at the modified code. We have a counter for the number of samples we've taken and the number of samples that we are going to take, which is the 200. We've got some variables for capturing the time when we start our run of sampling and when we finish. We have a prescaler value. This interval thing here could be left out. That's just a hangover from the Excel thing I forgot to delete. And we have the threshold voltage of 2, which is what we're going to measure as we go below and up each time it crosses that, we are going to then be setting this below threshold from false to true and updating this count of cycles. All of this stuff here, we're enabling the 2 pins for outputting our forward and backward signals. And this setup here is how we get the analog to digital converter set up and going without using the digital read function. And this is a faster way. This website here describes a lot more detail about it. It is definitely worth a look. This is also part of that code, so this is the interrupt routine that gets called every time the converter finishes taking a sample, and we then put that sample into the array of samples and update the index of the array. And then at the beginning we kick off the sampling. In our looping code we check whether we've got all of our 200 samples yet, and then we work through our array and capture the voltage by converting it from the single byte value that it is in the analog to digital converter, multiplying it and dividing, etc., so that we get a portion of 5 volts, which is the range that the analog to digital converter can measure. And then we detect if we are below the threshold, and if we are, we set our below threshold. If we detect if we were below the threshold and we've now crossed and are above it, and if we are, we update our count by 1 and we indicate that we're no longer below the threshold. Then anytime we cross back down below that 2 volt threshold, we set the below threshold flag to true, and we output, we turn on and off both of our outputs. We turn them to low temporarily, which means we're going to be signaling nothing, and then we increment the number of samples. Then once we've got, and the reason we do that is so that it will call this next piece of code, which checks if we have number of samples 1 higher than the 200, so that this code will run. And this will say if the number of cycles we detected was 2, then we'll output high on digital 2, which is going to be our reverse signal. And if we had more than 4, then we'll output high on the forward signal instead. And that's pretty much it. Okay, we've finished modifying the code, and we just got 2 LEDs now. We've got blue for forward, red for back. And let's set our frequency gen for 600 Hz. Coco's checking on the scope. Red light, let's go up to 1200 Hz. Blue light. Red, blue. Okay, that's it for this video. I've put the code in the GitHub repository, and there'll be a link to that in the description. And you can check out the playlist, 27 Mhz Radio Controller Receiver, for the other episodes, or if you want to go have a look at the Excel Oscilloscope, that's also there. Thanks very much for watching. I hope you had a good time. Bye.